Hello students, today we are going to derive the stiffness equation for a freely supported beam AB subjected to a couple M at B. Now a beam AB is shown here, that is this beam whose span length is small l and is subjected to a moment M at B. Now due to this movement, the deflected shape of the beam will be like this, and this rotation will be known as theta B. Now to resist this movement, we need to generate the reaction, that is this reaction. Now the reaction value will be equals to the net moment acting at the beam, that is M, divided by the span length, that is L. So it will be equals to M by L. Now the moment is acting in the clockwise direction, so we had to resist it by an anti-clockwise couple. So the reaction direction is like this. At support B, its direction is upward, and at support A, its direction is downward. So it will create an anti-clockwise movement like this. Okay students. Now for finding the stiffness equation, we need to take a section XX here whose distance is x meter from support B. Okay students. Now for finding the stiffness, we need to write the slope equation, that is EI d square y upon dx square. It will be equals to the net moment acting at section XX. So it will be equals to m by L into x minus m. M by L into x is because of this support reaction, and minus m is because of this moment acting in opposite direction of the moment produced by m by L support reaction. So it will be represented by minus m. Now we need to integrate this equation. On integrating it, we will get EI dy by dx is equals to m by L into x square by 2 minus mx plus c1. Okay students. Now we again integrate this equation and we will get EIY is equals to m by L into x cube by 6 minus mx square by 2 plus c1x plus c2. Okay students. Now we need to use the boundary condition here, that at x equals to 0, y is equals to 0, because no deflection of support B is given in the downward direction or in the upward direction, that is the vertical displacement. So it will be equals to 0. On putting this condition in equation of EIY, we will get EI into 0 is equals to 0 minus 0 plus 0 plus C2. So it will be equals to C2 is equals to 0. Now we had find the value of C2 as 0. Now we need to use the next condition, that is at x equals to L, y is equals to 0, because there is no vertical displacement of support A. So y will be equals to 0 at support A. So at x equals to L, y is equals to 0. Now we need to put this equation or this condition in the EIY equation, and we will get EI into 0 is equals to ml cube by 6l minus ml square by 2 plus c1l. On solving this, we will get c1 value as ml by 3. Now we will put this value in equation of EI dy by dx, which is like this, that is EI dy by dx is equals to mx square by 2l minus mx plus c1. On putting the value in this equation, we will get EI dy by dx is equals to mx square by 2l minus mx plus ml by 3. we will get the equation of ei dy by dx. Now at x equals to 0, dy by dx is equals to theta b. We had already seen it, that the deflected shape of this beam is like this, and at x equals to 0 it means that at support b the rotation is theta b. So at x equals to 0, dy by dx is equals to theta b. On putting this value in the above equation, we will get ei theta b is equals to ml by 3. On solving this, we will get m by theta b is equals to 3 ei by L. Now we need to find the stiffness of this beam, so it will be equals to moment required to produce unit rotation, so the stiffness of the beam will be equals to 3 ei by L. So whenever the far end of the beam is hinged, then the stiffness of that beam will becomes 3 ei by L. So we had derived a condition here that whenever the far end is hinged, whenever the far end is hinged, stiffness of that beam will becomes 3 ei by L. That is all about this derivation. We had derived the stiffness of that beam, which will be equals to 3 ei by L. Thank you very much, students.